class we have discussed about feedback amplifiers. Once again, I'll repeat about feedback amplifier. Okay. What is feedback amplifier? Okay. First, we should know the definition. What is feedback amplifier? If an amplifier has a feedback path exists from output to input, then that amplifier is termed as or called as feedback amplifier. Okay. If amplifier has a feedback path means from where it exists. It exists from output to the input. Okay, it exists from output to input, then that amplifier is termed as feedback amplifier. Okay, you can observe here from output to input, this is the feedback line. Okay, this is the feedback path. This is the feedback path. Next, types of feedback amplifier: positive feedback, negative feedback. For positive feedback, you can observe here positive symbol is there. So positive feedback, here negative symbol, so negative feedback. Okay, from output to input, here for negative terminal it is connected, here for positive terminal. Next, classification of amplifiers: voltage amplifier, current amplifier, transconductance amplifier, and transresistance amplifier. You can think what is these all. Okay, classification of amplifiers: voltage, current, transconductance, and transresistance. For voltage amplifier, input is voltage and also output is voltage. Okay, for voltage amplifier, it is output voltage is proportional to the input voltage. Okay, you can observe here when Ri is greater than Rs, then Vi is equal to Vs. Okay, it is almost equals to Vs. For this case, okay, if R naught is less than RL, then V naught is equal to AV into Vi, that is equal to AV into Vs. From this we can write AV is equal to V naught divided by Vi. That is what voltage amplifier. Next, current amplifier. Current amplifier, this is the diagram or circuit diagram of our current amplifier. Same here also. In last case, we have considered Ri is greater than Rs. Reverse of voltage amplifier. Okay, reverse of voltage amplifier. These two conditions you make reverse. Okay, Ri is less than Rs, then Ii is equal to Is. If R naught is greater than RL, then I naught equals to Ai into Ii, that is equals to Ai into Is. From this we can write Ai is equal to I naught divided by Ii. Okay. Next, transconductance amplifier. Okay. Transconductance. Transconductance means input is voltage and the output is current. Okay, here input is voltage and the output is current. You can observe here, this side voltage we consider and this side current. Okay, you can observe here two resistors are in parallel, that means current. Okay, here Ri is greater than Rs. Vi is equals to Vs when Ri is greater than Rs. Okay, these two resistance are in series. If this is similar to voltage amplifier. Okay, in voltage amplifier, starting case is Ri greater than Rs, that we have considered. But output side is current amplifier. So this condition we need to consider. R naught is greater than RL, then that is the case. I naught is equal to what you'll get? Gm into Vi. That is equal to Gm into Vs. Gm is equal to, you'll get I naught divided by Vi. Okay. Here trans conductance is input is voltage and the output is current. Okay. Next, trans resistance. Here input is current, output is voltage. Okay, here input side is current, means these two resistors are in parallel. Then what we should consider the case, that is Ri is less than Rs, because in current amplifier what is the condition here? Ri is less than Rs. Okay, that condition you need to consider because input side is current. Okay, so Ri is less than Rs, then that is the case IEI is equal to Is or equals to Is. Output side voltage. So R naught less than RL, V naught equals to Rm into II, that is equals to Rm into Is. Rm is equal to V naught divided by II from this equation. Okay. Next, amplifier. When you compare four amplifiers, voltage, current, transconductance, trans resistance, input resistance for voltage amplifier infinity, for current 0, for transconductance infinity, for trans resistance 0. R naught output resistance for voltage 0, for current infinity, for transconductance infinity, for trans resistance 0. Transfer characteristics. V naught is equal to AV into Vs. I naught is equal to IL is equal to AI into Is. I naught is equal to IL is equal to GM into Vs. V naught is equal to Rm into Is. This is what transfer characteristics. Next, concept of feedback. Okay, concept of feedback: signal source, input. Next, comparator or mixer network. Next, basic amplifier, forward transfer gain, sampling network. Again, from output to input side, that is feedback network, reverse transmission, beta. Okay, this is feedback. Okay, this all feedback. In sampling, there are two types, that is, one is voltage or node sampling and current or loop sampling. In voltage or node sampling, in this type of sampling, the output is sampled by connecting the feedback network in shunt across the output. You can observe here the voltage feedback. The feedback is connected in parallel form, or we call shunt. Okay, shunt across the output. It is connected in parallel. Okay, it is connected in parallel with the output. Here, current or loop sampling. It is feedback is connected in series with the output. Okay, feedback network is connected in series with the output. This is what current or loop sampling and voltage or node sampling. Next, to feedback network. The feedback network is usually a passive two-port network which may contain resistors, capacitors, inductors. Vf is equal to beta into V naught, where beta is a feedback factor or a feedback ratio. Next, mixer network. In this also two types, series mixer and shunt mixer. You can observe here connection, if for example, okay, this is Vs, this is feedback. Okay, if this is the case connection, okay, from here it is connected some other equipment or anything, amplifier, okay, you can think amplifier here. This is amplifier and this is feedback. This is the series connection. You can observe here these lines, okay, from voltage source negative end to negative end, okay, again here from here to positive. This connection, series connection, that is a series mixer. Here shunt connection, you can observe here from positive to here it is connected and from negative to here, okay, this connection is shunt mixer connection, okay. Next, transfer ratio or gain. The transfer ratio V divided by VI is the voltage amplification or the voltage gain, that is AV. Transfer ratio I0 divided by II is the current amplification or the current gain AI. The transfer ratio I divided by VI trans conductance, or that can be written as GM, and V divided by II is the trans resistance RM, okay. When you consider feedback, okay, without feedback means what we have written for voltage gain, you can observe V divided by VI, okay. For voltage gain, we have written V divided by VI. But when you consider here, when you consider the feedback, you will get V0 divided by Vs. So AVF, this instead of AV, we write AVF because we consider the feedback here. So AVF. Without feedback means only you will get AV, okay. V0 divided by Vs is equal to AVF, that is voltage gain with feedback. Next, I0 divided by Is, that is AIF, current gain. Current gain with feedback. If current gain without feedback means AI, okay. I0 divided by Vs is equal to GMF, trans conductance. Trans conductance, input is voltage, output is current, okay. V0 divided by Is for trans resistance. Usually for resistance what we will write, R is equal to V by I, okay, that is what here. But here we are considering the feedback, so output voltage, and we consider the source current, okay. So V0 divided by Is is equal to RMF, okay, trans resistance with feedback. Next is feedback topologies, okay, feedback network topologies or feedback connection topologies. Feedback network or these are feedback connection network topologies or feedback network topologies. First is voltage amplifier with voltage series feedback. Okay, we know that voltage amplifier. For voltage amplifier, how we will connect here? For voltage amplifier, we connect in parallel. Okay, you should know the connections. You can observe here voltage sampler, okay, how we have connected, okay, it is in parallel, okay. So they have said voltage series feedback, that means output side is voltage sampling and input side here series mixing, okay, series mixing feedback, okay. This is what voltage amplifier with voltage series feedback, okay. Next, here voltage amplifier with voltage and with series feedback. Next is transconductance amplifier with current series feedback. Okay, this is the current sampling. Okay, once again I will show current sampling. This is the current sampler dagger. Okay, how they are connected? The two connections are in series. Okay, in current sampler output side. So you can observe these 2 points are connected in series for output. Okay, this is a current. What about series? Here series mixing. Okay, this is here transconductance we use. Okay, so transconductance amplifier with current series feedback. Okay, next is current amplifier with current shunt feedback. Okay, current amplifier with current shunt feedback. You can observe here current sampling. It is connected in series and shunt feedback. Okay, shunt mixer or mixing. Okay, this is the type of connection, shunt and feedback. Okay, current amplifier with what? Current shunt feedback. Next, trans resistance. Same. Okay, voltage we use just here instead of amplifier we use the trans resistance amplifier. Okay, here we use the, here in this case instead of mixing they have used the shunt sampling. Okay, how you can use the shunt mixer? Here they have used voltage sampling. Okay, mute ಮಾಡಿ ಆಯ್ತಾ? Next, frequency distortion. AF is equal to 1 divided by beta. We can say that if the feedback network does not contain, if for example, if feedback network does not contain any reactive elements, then what happens? The overall gain is not a function of frequency. Under such conditions, the frequency and phase distortion is reduced. Okay, phase distortion will be reduced. If beta is made up of reactive components, the reactance of these components will change with the frequency. Okay, mute ಮಾಡಿ. Who is that? ಚೈತನ್ಯ ವ್ಯಾಸ್ ಮ್ಯೂಟ್ ಮಾಡು, ರೆಕಾರ್ಡ್ ಮಾಡ್ತಾ ಇದ್ದೀನಿ. If beta is made up of reactive components, the reactance of these components will change with the frequency. This fact is used in tuned amplifier. Okay, this fact is used in tuned amplifier. In tuned amplifiers, feedback network is designed such that at a tuned frequency beta is equal to 0 and at other frequencies beta will be infinity. Only they are saying that tuned amplifiers feedback network, how it is designed means, for tuned frequency beta will be 0. For other frequencies, for example at 10 kilohertz means if it is designed for 10 kilohertz, then it will beta will be 0 for 10 kilohertz, and for other frequencies beta will be infinity. Okay, as a result amplifier will provide a high gain for signal at a tuned frequency and relatively reject all other frequencies. For example, if you take if you take any signal or amplifiers, where we use amplifiers. Okay, usually we use amplifiers for speakers, loudspeakers. Okay, for some signals only you'll get some channels. Okay, when you only some frequencies, at particular frequency only the output of the product output of equipment will be run. Okay, for other sequences what happens, it will not get any signals or it will not give any output. Okay. Next, noise and nonlinear distortion. The factor 1 plus beta A reduces both input noise and resulting nonlinear distortion for considerable improvement. The noise and nonlinear distortion also reduced by same factor as the gain. Next is effect of negative feedback on gain and bandwidth. AF BWF is equal to A into BW. AF is a gain with a feedback, A is a gain without feedback, BWF is a bandwidth with feedback, BW is a bandwidth without feedback. What is the difference? Okay, BWF is equal to A divided by AF into BW. AF is equal to A divided by 1 plus beta. Okay, this is plus for negative feedback and minus for positive feedback. AF divided by A is equal to 1 plus 1 divided by 1 plus A into beta, or A divided by AF is equal to 1 plus beta. We know the value of A divided by AF, substitute, so you will get BWF is equal to 1 plus beta A into BW. So 1 plus beta A is greater than 1, by BWF is greater than BW. Bandwidth will increase by a factor 1 plus beta A. Okay, bandwidth will with the feedback will depend on 1 plus beta A. Okay, as it is gain, this depends on this. Okay, so A naught is a mid-band gain. Okay, in this diagram or a graph, A naught is a mid-band gain. A naught F is equal to A naught divided by 1 plus beta into A naught. BW is equal to F2 minus F1. BWF is equal to F2F minus F1F. Okay, this is the graph for that. F1F less than F1, F2F is greater than F2. Next, gain stability with feedback. DAF divided by AF is equal to 1 divided by 1 plus beta A. DA divided by A. DAF is divided by AF equals to this 1 plus beta can be written as beta A. So, because for beta A greater than D is a fractional change in amplification with feedback. dA divided by A is a fractional change in amplification without feedback. Change in the gain with feedback is less than the change in the gain without feedback by a factor 1 plus beta A. Okay, change in the gain with the feedback. Okay, change in the gain in gain with the feedback is less than the change in gain without feedback by a factor because of 1 plus beta A. Sensitivity of transfer gain, that is DAF divided by AF whole divided by DA divided by A, that is 1 plus beta A. Desensitivity is equal to 1 divided by sensitivity. If you substitute the value, you will get 1 plus beta A. But usually beta A is greater than 1. So if we can write it as beta A get cancelled. So you will get 1 by beta. So gain is dependent only on the feedback network. AVF is equal to 1 divided by beta, that is voltage gain is stabilized. GMF is equal to 1 divided by beta, transconductance gain is stabilized. RMF is equal to 1 divided by beta, trans resistance gain is stabilized. AIF is equal to 1 divided by beta, current gain is stabilized. Okay, in next class, I will explain about the practical feedback circuits.